Okay, so let's say that x comma delta is KLT, and f from x to y is a projective morphism, and we'll keep our running assumptions from about a month ago, which were that all varieties are connected quasi-projective normal for now. Well, then I won't rewrite all the statements, but basically all the statements of the Cohen theorem hold true, where you replace any of x with any x over y. So, or maybe I'll just summarize them. Then, one, we have that any x over y is any x over y kx plus delta non-negative plus a sum that's countable of rays spanned by rational curves. 2 for epsilon greater than 0 and h ample. We have the same type of decomposition, but with a finite sum. And here, of course, h is f ample. Where we perturb by a small amount of h. Three, let's say contractions of kx plus delta negative extremal faces exist. And are unique. So again, where a contraction is a morphism, where phi of c is a point if and only if c is in this face and phi lower star O is O. And then 4, again, same as before, line bundles that are trivial, say numerically trivial, on an extremal face are pulled back by contraction. Okay. Great. So let's prove this. But again, we'll just sketch it just like the proof of the relative base point free theorem. So step 1, just like in that case, is compactify x and y and f to be a projective morphism between projective varieties. and then extend the divisors appropriately to the boundary so that all the assumptions are still satisfied. So the singularity assumptions is still satisfied. Okay, and now step 2. This is maybe the important observation. So if we have some class psi that's in this negative piece of the cone, of the relative cone, well, let's write it as eta plus sum of Rj class of Cj, where these are the Cj appearing in the usual cone theorem, because now we've projectivized. Now we've compactified so that x is projective, and we can just apply the cone theorem on x. And maybe this proof also maybe tells you why it's still kind of the absolute canonical rather than the relative canonical, because we're going to apply things to x still. So write it down like this. So where these Ci are the generators of the kx plus delta negative rays inside of the full cone of curves now. And this sits inside of the kx plus delta non-negative piece. Okay, and so we can write it this way by the cone theorem applied to x. Okay, and now we know that the push forward of this psi is 0 because it's contained in the fibers. Right, so but by definition, psi is some pseudo-effective class in the fibers of F. So when we push it forward, we get something 0. But on the other hand, this is the same as the push forward of eta plus some Rj push forward of these curves, Cj. And now the other observation is that because psi is pseudo-effective and these Cj are actual generators for this cone, then the Rj are non-negative, or strictly positive, in fact, because we're assuming some negativity about this psi. So in fact, some of the R's have to be strictly positive. So these are strictly positive. When we push forward, we get 0. But the push forward of eta, this is some other pseudo-effective class. So this is, if we push forward something pseudo-effective, then it's going to be pseudo-effective downstairs, because if we write it as a limit of effective classes, we push those forward, they're still effective, and then their limit will be the push forward. So this is effective or pseudo-effective downstairs on y. And so we have this combination, and so are these. This is pseudo-effective, and so are the push forwards of the C's. But we have this convex combination of pseudo-effective classes, and it's equal to 0. The only way that could be the case, because y is projective as well, so y contains the cone of y contains no lines either. So we said that on a projective variety, the cone is kind of strictly inside of a half space, because it's inside the half space cut out by any amples, so it can't contain any lines. And so if we have this non-negative convex combination of pseudo-effectives, but it's equal to 0, then each of the terms have to actually be 0. So since y is projective, any y contains no lines, so each of these terms must be 0. Okay, and so that means that we've written things. We took some class that was some pseudo-effective class that's contracted by f. We wrote it down using the cone theorem on X, and then when we push forward, we checked that actually the way we wrote it down has to already be a decomposition inside of the relative cone, because both the eta and the CJs are contained in the fibers of F. And so we conclude then that every curve in any x over y, kx plus delta, just any x over y, can be written as a sum of a kx plus delta non-negative curve that's contracted by f, or class that's contracted by f, plus a sum of these rays spanned by the subset of the rays in the usual cone theorem of rays satisfying that the push forward is 0, i.e. that they're exactly in the fibers. Okay, so that gives us the first part of the cone theorem, that the relative cone can be written as the relative cone where things are non-negative plus a sum of rays where kx plus delta is negative and that are contracted by f. Okay, so that. And of course, since these C's are a subset of the curves for the full cone of X, then they satisfy all the nice properties that the curves in the usual cone theorem satisfy. These things we didn't prove, that they're rational curves and that they have this bound on the intersection with kx plus delta. And then the thing we did prove, that there are only countably many of them. Okay. So now we need to show that if you perturb by some relatively ample, then you get a finite sum. So let H be a relatively ample. And pick some epsilon greater than 0. So now, because we have this F ample, we can pick some ample on Y, so that when we pull back, we get something ample on X. So we might have to make A positive enough, so you might have to multiply by some very large M, but that's okay. And so by the usual cone theorem, we know that any bar X, kx plus delta plus epsilon H plus F upper star A. So here we've perturbed kx plus delta by some globally ample thing. So we only have a finite sum by the usual cone theorem. But now this F upper star A is 0 on all the curves in the fibers. So when we restrict it to any x over y, then we can ignore it. So basically, so any x over y, kx plus delta plus epsilon H strictly or greater than or equal to 0 is contained in the piece where kx plus delta plus epsilon H plus F upper star A is greater than or equal to 0. And so from there we can conclude, because then kind of this piece plus the finitely many curve, like the sum of the curves in this, so I don't want to say this, then from the decomposition previous, we know that to generate everything, we need to take a subset of these curves. But there's finitely many up here, so there's going to be finitely many that we need down here as well. Okay, so that was step 3. And then step 4 is just run through the same argument, because now we have the relative base point free theorem. So now we use relative base point free theorem to produce extremal contractions, just like before. And by definition, because we're using the relative base point free theorem, we have this relative semi-ample divisor, so all our contractions will be relative to y. So they'll commute in a diagram like this. And then continue just like before. Especially because once we produce phi r, which we produce from the relative base point free theorem, then for the last step, that doesn't care about y at all. The last step was about pulling back line bundles along phi r, and that just cares about phi. It doesn't care that we produce phi by taking a relative semi-ample series rather than a globally semi-ample linear series. It just cares that we have this phi. Corollary, relative and therefore absolute, because the absolute case is when y is a point. So the relative cone theorem holds for DLT pairs, not just KLT pairs. And this is really the reason that DLT pairs are nice, because we know that, I mean, we can't avoid having some coefficients 1 when we're working with pairs. You take some resolutions and you have to pick some coefficients to put. And there's other reasons that you can't avoid having some coefficients 1. So you know you can't always be in the KLT case in applications, but then this corollary tells you why DLT is really the right condition where you still have everything you want because it's close enough to KLT. Proof. Essentially, there's one observation, which is that if x comma delta is is DLT, then x 1 minus some small number, lowercase delta, times delta is KLT for any small enough delta. And then we take, like, if h is an ample and epsilon is some number greater than 0, then we just pick this small enough delta so that epsilon h so pick this delta such that epsilon h plus lowercase delta times our capital delta is still ample. We can do that. We just make delta much smaller compared to epsilon. And then we have that any bar x over b is, well, we apply the cone theorem to the KLT pair with 1 minus delta coefficient and with the ample being epsilon h plus lowercase delta uppercase delta. So we get that this is any bar x. And I guess I'll use the notation from the previous theorem. So we'll call it any bar x over y. Then any bar x over y is any bar x over y kx plus 1 minus delta delta plus our ample plus a finite sum of negative rays spanned by curves. But now here, okay, so here, because this was a KLT pair, but now we just rearrange this, and this is the same as any bar x over y kx plus delta plus epsilon h plus sum of finite number of these rays. And so we've proved that for a DLT pair, as soon as we perturb by a small enough ample, or by any amples, for a DLT pair, as soon as we perturb by an ample, we get a decomposition with a finite sum of negative rays. And then just like in the proof of the original cone theorem, once you have this, then you take the limit as epsilon goes to 0, and you get a countable sum for any bar x over y. So, and then plus argument as in the proof of the cone theorem. Or often abbreviated as LMMP, or sometimes just the L is even dropped because usually nowadays, whenever people talk about the minimal model program, they'll have divisors floating around naturally. And of course, it contains the minimal model program as a special case where you just don't have a divisor, or where delta is 0. So we have our pair x comma delta, and let's just recall very briefly what we wanted out of the minimal model program when delta was 0 to guide what we want in the log case. Well, in this case, we said that a minimum model was a XM with a birational map from X to XM, such that XM has terminal singularities let me actually write this a little more systematically, so such that 1 XM has terminal singularities, 2 KXM is Neff, and 3 phi is birational. Okay, so that was our definition of a minimal model in the absolute case, and then the same thing for a canonical model. One XC has canonical singularities. 2 KXC is ample. And 3 phi is birational. And then finally, in this case, in this canonical model case, assuming some conjectures, we expected that XC is proj of the canonical ring. And this is the abundance / finite generation. Okay, so that's what we wanted in the absolute case, and now we've generalized to this case of pairs. So how did we get to this point? Well, we said that we apply extremal contractions. Sometimes we have to do flips, and so we need to talk about flips in the log setting. And then we assume that we can keep applying extremal contractions from the cone theorem each time. So then we need to know that after every extremal contraction, we can still apply the cone theorem again. So we need to know something about the singularities, that they don't get worse. And then we had to, then the conjectures are that this sequence of extremal contractions will terminate into something that's either a minimal model or is an extremal contraction over something lower dimensional. And then this abundance conjecture tells us that when we have this minimal model, then we also have this canonical model. So that was kind of the logic of it, and now we want to rewrite the same kind of goal in this log setting. So so the LMMP Usually people write it as some kind of as an algorithm. So let me try to write it that way. So our input is a projective morphism. So we're gonna do it here in full generality where we have a pair and we have a morphism, so it's relative as well. So a projective morphism, again, X and B are running assumptions, connected, quasi-projective, normal. So I won't rewrite those. And with the assumption that one, X comma delta is DLT, and two, X is Q factorial. So this is a simplifying assumption. So we already saw we needed this Q factoriality to argue that, for example, if we contract an extremal ray and it's divisorial, then there's unique divisor, for example, which gave us that the Picard rank drops by 1. So we need this Q factoriality for for technical reasons, but we also saw that Q factoriality is preserved under divisorial and contractions and fiber spaces. So it's not too bad. And also in practice, you'll usually start with a normal crossings pair, X comma delta anyway, or a simple normal crossings pair. So that's our input. And then we have the algorithm itself. So pick some pick a kx plus delta. Well, maybe I should say first set yeah, let's set our first pair to just be x comma delta, and then assume we have xi, then pick a kxi plus delta I negative extremal ray. In any bar x over y, and then apply this extremal contraction. If it's divisorial or if it's divisorial, just you have the extremal contraction. If it's a small contraction, we have a flip. So let phi I from xi to xi plus 1 well, okay, let me say it this way. If phi r is not a fiber space, so it doesn't contract to something smaller dimensional, then we let phi I be the morphism, be either phi r itself or be the flip of phi r. And we'll say more precisely the definition of a flip in this log setting. And we let delta I plus 1 be the push forward of delta I. And now what do we need to keep going? Well, then we need to know so assuming these flips exist, then we need to know that after we contract or flip, then xi plus 1 is q factorial, and that the pair is still DLT. And so now, as long as we don't have a fiber space, we just keep inputting into this until we're done. When are we done? we're done when we either end up in a fiber space and then we're something lower dimensional, and we hope that we can understand that easier because it's lower dimensional, or we end up with something where kx plus delta is relatively nef, and then we have no more extremal rays. So, so the output is either a Mori fiber space, or this log Fano fibration of Picard rank 1, and let me call it xn for kind of the last step in our program, assuming that it's finite. Or a model xn delta n where kxn plus delta n is nef over our base, so it's f nef. Okay, and then once we have our model, then we can ask whether the abundance conjecture holds, so whether it's actually semi-ample, and then we know that in the case we showed that the base point free theorem, assuming the singularities of xn delta n are nice, so assuming that we've already taken care of this the question in red, which we'll do in a few minutes, then in the case that kxn plus delta n is big, say, and the singularities are nice, then we already showed that that we do know no abundance in that case. Okay, so that's our log minimal model program. So the main things to keep in mind are that we need to check Q factoriality in this DLT condition, and that the right divisor to put downstairs is the push forward of the divisor upstairs. And there's actually some subtlety here. The point is that these phi i's, they never extract divisors. So extract divisors is like a technical way of saying that the inverse of phi I doesn't contract divisors. So give a remark here. At least the phi that are birational in this intermediate kind of in the actual algorithm, and that's important because if you were ever dealing with birational morphisms that do extract divisors, then you have to be more careful. You can't just let delta be the push forward of the divisor, because that's kind of ignoring all the information about the exceptional locus of phi inverse. And there are examples. There's kind of an easy example where if you don't take care about for these extracted divisors, if you don't add some coefficients there, then you're actually changing the log canonical ring. And of course, we don't want that because we want our final log canonical models to be proj of the log canonical ring. We want that to be well defined. So we don't want our log canonical sections to vary as we go. So as an example, I'll let you check this on your own, but if you take P2 with 3 lines intersecting in the usual way, 3 coordinate lines, and then take well, we'll call this G to be the blow up at a point, say at one of these intersection points, say over here. Of P2, and then let D be maybe D prime be G lower star inverse of D, so the strict transform of D where these 3 lines are divisor downstairs. Then this is a case where G inverse does extract a divisor. It extracts the exceptional divisor, and the point is here in this example, well, downstairs, there's one pluricanonical section because the canonical of P2 is O minus 3, and we're adding 3 lines, so the log canonical is just O. So we just have one section. But upstairs, we actually have no sections because we haven't added back the exceptional divisor. If we just take the strict transform, there are actually no more sections because we've added this negativity by not adding back the strict transform. So in this example, the pluricanonical sections are different. And so if you want to understand birational maps between pairs that do extract divisors, you have to be careful about what coefficient you put on the extracted divisors. And usually the right coefficient is 1. Because if your pair downstairs has log canonical singularities and you put coefficient 1, then the definition of log canonical singularities guarantees that that's not changing the sections. That was the whole point of log canonical singularities. But okay, so that's a subtlety that we can avoid when running specifically this program because these phi are nice. Okay. Any questions? Okay. So now I guess we should make formal what a flip is in this log situation. So our definition, a kx plus d. So now if we have any pair x comma d, we can define a flip more generally. So kx plus d flipping contraction. Is a small birational morphism f from x to y. Usually here, not always, different authors have different conventions, but usually here we add the assumption that the relative Picard rank is 1, which comes for free when this is a contraction of an extremal ray. So an f from x to y, sometimes with Picard rank 1, such that minus kx plus d is f ample. And then the flip of f is a morphism f plus from x plus to y, such that, let's draw a diagram. So we have x, we have our flipping contraction f from x to y, we have our flip f plus. Let's give a name to this birational map here, call it phi. Then a flipping contraction is something that sits in this diagram such that, the flip of our flipping contraction is something that sits in this diagram such that 1, the push forward of d, which we'll call d plus, how do I say this? Well, this is some Weil divisor a priori. We needed to satisfy that kx plus d plus is Q Cartier. That's the first thing. Otherwise, we can't make sense of much. And here, of course, I should have assumed, I didn't really write the assumptions in this definition, but I should have assumed that we have some pair where kx plus d is Q Cartier. So it makes sense to talk about it being relatively ample. Okay, so if we take our push forward of d, this d plus, then it satisfies that kx plus d plus is Q Cartier. And then again here, because f and f plus, well, f is small, and I haven't said yet that f plus is small, so let me add that. The second condition is that f plus is small. So because f and f plus are small, then this phi does not extract any divisors, and so we're safe to define the divisor on x plus to just be the push forward, or the strict transform, essentially, because when phi is a small map that extracts no divisors. They're the same thing. So we're safe to do that because we also assume that f plus is small. And then the last condition, well, we had something where minus kx plus d was ample. Now we want k plus d to be ample. So. And then of course x plus is normal and f plus is projective, the usual assumptions. Okay, so that's the definition of a flipping contraction and of the flip f plus. We'll see next week that flips, if they exist, are unique, and then we'll talk a little bit about when do flips exist. And you should think of this as kind of, I have this curve that I'm cutting out using my extremal contraction. This because we're assuming this Picard rank is 1, so we essentially are losing exactly one curve class, and then we're gluing in a curve class that has like the opposite normal bundle. It's not really the normal bundle; it's really the restriction of k plus d. So that's, I don't know why it's called a flip. Okay, any questions about that definition? Okay, and so assuming that all small contractions of extremal rays admit flips, then our algorithm makes sense. And then assuming that every sequence of flips terminates, which we actually don't know still, then our algorithm terminates and gives us an output in finally many steps. Okay, so then to summarize what we have, what one would want to carry out the log minimal model program, we still need to check the singularities are nice after every step, and then you want to know that flips exist, and you want to know that sequences of flips terminate. Okay. So the first step is to check this Q factoriality for flips. So we already checked that Q factoriality is preserved under divisorial contractions and is also preserved under that last Mori fiber space contraction. I think we proved this last time. So we need to check the same thing is true for flips. So let x comma delta be a Q factorial DLT pair. Let phi be a small, well, let's just say it this way, let it be a contraction of an extremal ray that's also a flipping contraction. And suppose that we have a flip. Then 1, x plus is also Q factorial. And 2, the Picard rank of x is equal to the Picard rank of x plus. So you should think of it as phi drops the Picard rank by 1, because the relative Picard rank of phi is 1. And then also the relative Picard rank of phi plus will be 1 as well, because we're cutting out one curve and gluing back in this one, exactly one new curve class, and so the Picard rank actually stays the same. And this is the main issue with termination of flips. If we knew that the Picard rank of x plus was smaller, I mean, of course it can't be because we're gluing in a new curve. But that's exactly the issue. If we knew that it got smaller, then we can have termination exactly like we did for surfaces, but it doesn't. We'll see some other invariants do get smaller, but it's not so clear how to use them to prove termination. Specifically, we'll see discrepancies get smaller under flips, or get bigger. Discrepancies get better. The singularities get better. Okay, so proof. Let's draw our flipping diagram. We have x to y, we have x plus to y. Here we have phi r, here we have phi r plus. Let's just call this birational map phi. Let me use the other phi to be less confusing. Let's call it var phi. So what do we know? We know that phi is small and birational. And so if we take a Weil divisor, or even a Q Weil divisor on x, well, we have the push forward by phi. That gives us a Q Weil divisor on x plus. But phi is small and its inverse is small. So actually, if we push forward the other way, we get the same Weil Q divisor we started with, because we just take the x and x plus are isomorphic on some open set that has complement codimension 2 on both x and x plus. So when we take the closures, everything's uniquely defined. So Weil divisors on x are actually isomorphic to Weil divisors on x plus, just by the maps phi lower star and or var phi lower star and var phi inverse lower star. Small birational and extraxional divisors. Okay, so Weil divisors are the same on both sides. So if we let d plus be some Weil divisor on x plus, to prove Q factoriality, we need to show that d plus is Q Cartier. So we consider, I keep writing the wrong phi. I guess I should have used a different letter. We consider the strict transform inside of D, inside of X, call this D. And now we use that X is Q factorial, but that's not quite enough because we still need a way to compare the D plus and the D in a way that preserves Q factoriality. So we need to go through Y, because if we go through Y, there we have actual morphisms, and so we can compare line bundles. So to go through Y, we need to modify D so that it's pulled back from Y. Well, how do we do that? We add some multiple of the log canonical divisor, because we know that kx plus delta is f anti-ample. In particular, its intersection with the fibers of phi r are not zero. D has some intersection with those fibers, so we can pick a coefficient where this thing is zero on the fibers or on our extreme array. So there exists an R so that thing's zero. But then by the cone theorem, we know that we have a divisor dz, a line bundle, in fact, or a Cartier divisor, m times dz, so that phi r upper star of m dz is equal to m d plus r kx plus delta as line bundles. So I really should put linearly equivalent here. Okay, because so this m is just here to clear denominators to make it Cartier. Okay, but now we just compare the two sides. So, and I'll just divide by m and use Q linear equivalent. So, we have that D plus is equal to the push forward of D, which is linearly equivalent to the push forward under var phi of the pullback of dz minus the push forward of M R kx plus delta. Right, but then the push for like this phi lower star, phi upper star on dz is just the same as phi plus upper star dz. Again, because everything's small, and so at each step we're just taking the closures of divisors. But on the other hand, dz is Cartier or is Q Cartier, so when we pull it back, we still get something Q Cartier. Here we get the push forward of the log canonical, but this is just the log canonical on x plus, which by the definition of a flip is Q Cartier. And so d plus is Q Cartier. So here we have Q Cartier, and so d plus is Q Cartier. Okay, and then now once we know that everything is Q factorial, then we get the Picard rank statement because we already know that Q of A divisors are isomorphic, and if everything is Q Cartier, then that just tells us that Q Cartier divisors are also isomorphic, so the Picard rank is the same. So the Picard rank is the dimension of the space of Q Cartier divisors. Okay, cool. Great. So we have the first part, which is that Q factoriality is preserved. Now we need to know that the discrepancies also don't get worse. So that's the last thing. So we need to know that that after every extremal contraction or flip, the discrepancies can only increase, and so the singularities can only get better and not worse. So let's say we have some x comma delta. I don't want to assume yet it's KLT because we want to say kind of if it's KLT, then after a flip or contraction, you still get something KLT. If it's DLT, then after a flip or contraction, you still get something DLT, etc. So let's say we have some pair x comma delta with delta effective. And let G from x to x prime be either a divisorial extremal contraction or a flip of a small contraction. Then for any divisor, or maybe just more succinctly, then x comma delta is KLT, respectively log canonical, respectively DLT, implies that x prime with the push forward along G of delta is KLT, respectively log canonical, respectively DLT. Okay. Proof. So the proof boils down to the following lemma, which tells you how discrepancies change. And to combine the two situations, we're just going to draw a diagram that looks like a flipping diagram, but if one of the sides is the identity, then it's just an extremal contraction diagram. So let's suppose we have a diagram that looks like a rational map phi from pair x comma delta to a pair x comma delta prime. Both of these lying over a y with maps g and g prime, where these are actually morphisms. And let's assume that g and g prime are projective, that g lower star delta is delta prime. Sorry, that g lower star of delta is g lower star of delta prime because g and g prime map to y. Two, that minus kx plus delta is q Cartier and g nef, and that kx plus delta is q Cartier and g prime nef. So note there's a minus sign for g and there's no minus sign for g prime. Then for any exceptional divisor, E lying over Y, the discrepancies for the pair x comma delta, or the discrepancy of this divisor for the pair x comma delta is less than or equal to the discrepancy for x prime delta prime. And then moreover, if we assume something slightly stronger, so here the assumptions are definitely weaker than we need. So we're only assuming nefness for both g and g prime. In the case that phi is a flip, then both these will be ample. In the case that we have a divisorial extremal contraction, then g prime will be the identity, and g will be the extremal contraction, and g will equal phi. And then again, in 2, we'll have that minus kx plus delta is g ample. So in our actual applications, we'll have a little more, and so if we do have that little more, then we actually get a strict inequality here. So if either minus kx plus delta is g ample and g is not an isomorphism along this E, essentially, if we assume that, or kx plus delta is g ample, sorry, kx prime plus delta prime is g prime ample. And the same assumption that g prime is not an iso at the generic point. So basically, if this E is really an exceptional for these maps, then we have strict inequality. Okay, but in any case, it tells us that in extremal contractions and flips, so in divisorial extremal contractions and flips of small extremal contractions, the singularities can only get better. And the second part tells us that they kind of strictly get better along the loci lying over the the exceptionals of our contraction. So kind of everywhere else, maybe they don't improve, but where our contraction is actually happening, they basically strictly improve. Okay, so proof of the lemma. So pick some z that dominates both. So we have this x and this x prime, so just pick some z, a hat on top of them. Like this, let's call this morphism f, this morphism f prime, and let's call the composition down to y h. And suppose that the center of E on Z is a divisor. So suppose we've picked some resolution of the rational map that actually pulls out this divisor E. So we really see E on this particular Z. So there always exists such a thing. And now let's just compare discrepancies. So if we look at discrepancies for X and Z, we get that KZ minus the sum of discrepancies EI is equal to the pullback of kx plus delta, and similarly kz minus the sum of the discrepancies for the primes is equal to the pullback of kx prime plus delta prime. And now we use our assumptions. So we're going to take the bottom equation minus the top equation. And then we get that the sum, well, we have minus signs in the bottom equation. We're subtracting the top one. So we have the discrepancies without primes minus the discrepancies with primes. Is equal to the difference of the prime pullback and the pullback of the unprimed. Okay, and let's just call this divisor B. This difference of discrepancy, actually, let's call it minus B. We'll see in a second why we want to take that convention. Okay, now what do we know? Well, we know that on all curves, like on Z, we have some curves that are contracted by f and f prime respectively. And on those curves, these pullbacks are 0. But we also know that on any curves contracted by G, this minus f upper star kx plus delta is strictly positive. And on any curves contracted by G prime, this kx prime plus delta prime is strictly positive. And so that tells you that on all the curves on Z, this difference has to be non-negative. So by our assumptions on the positivity of kx prime plus delta prime and minus kx plus delta, then this difference minus B is HNF. So again, we're only looking at curves that are contracted down to Z, and we're ignoring all the other curves. So if this minus B is HNF, but then we have this negativity lemma, which I kept avoiding stating precisely, and now maybe I can state it more precisely, which we've used all the time. Which says, well, intuitively what it says is that if we have some exceptional divisors, then they have to be strictly negative on exceptional curves, because kind of and the argument was when you slice down to surfaces, you have the Hodge index theorem, which tells you that. And more generally, so intuitively, what is that saying? It's saying these EIs are exceptionals over Z. And so if I know that this linear combination is Nef over Z, then these coefficients have to be less than or equal to 0. That's what the negativity lemma is saying. It's saying that if I have effective exceptionals, then I get something that's actually strictly negative on the exceptional divisors. Or more formally, what it says is that in this situation, where we have some linear combination that we called minus B of exceptional divisors over Z, then minus B Nef implies that B is effective if and only if the push forward is effective. So it's slightly more general statement, but in the case we care about, the push forward is actually just 0 because we're subtracting, like when we push down to Z, kind of kx plus delta and kx prime plus delta prime are the same. So the push forward is actually 0. So because minus B is Nef, then B has to be effective. That's what the negativity lemma is saying. Saying that effective divisors are actually negative on exceptional curves. So if minus is Nef, then and again, the proof of this, I won't write down the details, but it's this kind of argument where you slice down to the surface case, and then on the surface case, it's exactly the Hodge index theorem. Okay. And so now that tells us, so in our case then, because minus B is Nef, of course here it should be H Nef, we know B is effective. So that tells us that these coefficients are non-positive, which is exactly the inequality we wanted. So by negativity lemma, the AIs without the primes are less than or equal to the AIs with the primes. I don't know why I put the index twice. I really should just have A of EI. Okay, so that's the first thing we wanted to prove. And then the second thing is just that under our extra assumptions that either we actually have ample instead of Nef, and we know that the map is not an isomorphism over E, what that tells us is that this divisor minus B can't just be numerically trivial on E, because E is going to appear in the sum, and we're going to have one of these terms be strictly positive, and so we're going to have some curves where this minus B is strictly positive on the exceptional, and so the only way that can happen is if one of these is if the coefficient of E is not 0, because we're looking at the generic point. Everywhere else we have these other EIs, but those will intersect E in higher codimension, and our assumption was about the generic point of the center. So so under our extra assumptions, minus B restricted to E, or restricted to the generic point is not Nef. Sorry, is not trivial, is not numerically trivial. And so the coefficient the coefficient of E can't just be 0, and so we get a strict inequality. Okay, so that proves the lemma, and that essentially proves the proposition as well, with the one caveat, which I'll finish in like 1 or 2 minutes, which is that so this is it for the KLT case and the law canonical case, because in those cases, the definition is just in terms of discrepancies. The lemma tells us the discrepancies can only get bigger. And so if we have something KLT, then we have something, then then after on X primes, we're still KLT. If we have something log canonical, then X prime, we're still log canonical. The only thing to check is this DLT case where the definition was a little more subtle. So so if we have DLT, then we know that we have some, like by definition, we have some subset Z, where when we remove Z, we get discrepancies that are strictly, sorry, when we remove Z, we get something simple normal crossings. So our discrepancies are strictly bigger than -1 over Z, and then away from Z, we just have something S and C. So pick our Z such that X minus Z, delta minus Z is S and C, and let Z prime be the image under phi of Z union the exceptional phi inverse. So this sits inside of X prime. So look at wherever phi is defined on your Z, take its image, take its closure. That's what phi of Z means, and then take the exceptional of the inverse. So take everywhere that the inverse is not defined. That gives us some subset on the X prime. The first thing to note is that X prime minus Z prime is actually just an open subset of X minus Z because we're removing the exceptional locus. And so on X prime minus Z prime, we have an S and C pair. Or an S and C divisor. And so we just have to check that the discrepancies over Z prime are strictly bigger than -1. So let E be a divisor with center inside Z prime. Well, first we know by our lemma that the discrepancies are greater than or equal to 0 to the discrepancies of this E on X delta by the lemma, which are greater than or equal to -1 because it's DLT. So this is the first part of the lemma, and this is the DLT assumption.